Hello everyone, welcome back. In this video, I'll be covering section 4 of chapter 4, intermediate forms and L'Hopital's rule. Suppose we wanted to analyze the behavior of the function f of x equal to ln x over x minus 1. Note that although f is not defined at x equal to 1, we would like to know the value of the limit. What happens if x approaches 1? Because x minus 1 occurs in the denominator. When you plug in x equal to 1, it makes the denominator 0. And also the numerator becomes ln of 1. That becomes 0 as well. So it becomes 0 over 0 format. So what we want to do is what happens in the neighborhood of 1? What happens when x approaches 1 from the right side of 1 or from the left side of 1? So as it is, if you look at this, whenever we plug and play, so when we do limit as x approaching 1, ln of x over x minus 1, we try to plug in, we get ln 1 over 1 minus 1. ln 1 is 0, 1 minus 1 is 0, which is an indeterminate form. So in order to get an expression, in order to get a value, a definite value for this quotient, so we use L'Hopital rule. So what does the rule say? L'Hopital rule for quotients. Suppose f and g are differentiable and derivative of g of x is not equal to 0 on an open interval I that contains a point A except possibly at A. Suppose that limit is x approaching A f of x equal to 0. And also limit is x approaching A g of x equal to 0. And that limit is x approaching f of x equal to infinity or negative infinity. And limit is x approaching A g of x is infinity or negative infinity. In other words, we have a quotient of the form so we have the form indeterminate form of the quotient type, which is 0 over 0 or infinity over infinity. Then limit is x approaching A f of x over g of x equal to limit is x approaching A derivative of f of x over derivative of g of x. If the limit on the right hand side exists or is equal to infinity or negative infinity. Let's say example 1, limit is x approaching 1 ln of x over x minus 1. If you directly plug in this value x equal to 1 in here, it becomes ln 1 over 1 minus 1, which is 0 over 0, which is indeterminate quotient. Now we are allowed to apply L'Hopital rule. So limit is x approaching 1 ln x over x minus 1. Using L'Hopital rule, that's how we apply the L'Hopital rule. We write that way. Limit is x approaching 1, derivative of the numerator, just derivative of ln x over derivative of x minus 1. So it is limit is x approaching 1, derivative of ln x is 1 over x, and then derivative of the numerator is 1 over x. The denominator derivative is 1. So it is 1. Now you apply plug and play. Now you want to plug in x equal to 1 here. So it's 1 over 1 divided by 1, which is equal to 1. So what was earlier a 0 over 0 now becomes just the value 1. We'll take another example. Limit is x approaching infinity, ln x over square root of x. You directly plug and play, this limit is, so if you plug in x equal to infinity, so it becomes ln of infinity over square root of infinity. Both values are equal to infinity, because if you look at the graph ln x, as x approaching infinity, ln of x approaches infinity. So the numerator is infinity, denominator is infinity as well. It's again indeterminate quotient. Anytime you have indeterminate quotient, you can easily apply L'Hopital rule. So I'm applying L'Hopital rule, which means I have to take the derivative of the numerator, and then I take the derivative of the denominator. Derivative of ln x is 1 over x. Derivative of ln x is 1 over x. Derivative of square root of x is 1 over 2 radical x. So if you flip and multiply, you get 1 over x times 2 times radical x, which is 2 over radical x on simplification. Now, if you plug in infinity in the place of x, you get 2 over radical infinity, which is 2 over infinity, which is equal to 0. The final answer becomes 0 here. Let's say another indeterminate form, this indeterminate product. So if you are applying, if you consider limit as x approaching a of f of x times g of x, the product, then if one of them approaches 0, the other one approaches infinity, then it's neither 0 nor infinity. The product is neither 0 nor infinity. So in order to apply L'Hopital rule, we want to bring the product and write that as a quotient. So the way we do, let's say you want to do 2 times 3. What is the other way of writing this as a quotient? It can be written as 2 times 1 over 1 over 3 or 2 over 1 over 3. These two are one and the same. Same way, 2 times 3 can be written as 3 divided by 1/2. So that is a trick we want to use because L'Hopital rule can be applied only to quotients, which means something on the numerator over something on the denominator. So f times g can be written as f over 1 over g, or fg can be written as g over 1 over f. This converts a given limit of an indeterminate form of type 0 over 0 or infinity over infinity. So now we could apply L'Hopital's rule. So directly if you apply plug and play, it is 0 plus for x and ln of 0 plus. So it is 0, ln of 0 plus. What it means is what happens to the value of the graph ln x as you approach x to 0 from the right side of 0. So you notice that when you allow x to approach 0 from the right side of 0, ln of x actually approaches negative infinity. So it is negative infinity. So 0 times negative infinity is neither 0 nor infinity or negative infinity. So it is indeterminate product kind. Now we want to write this product in a different way. So before we apply the limit, we'll write like ln of x over 1 over x. We could have also written x over 1 over ln x. So anytime the problem has an expression ln x, it's preferable to have it on the numerator as opposed to denominator. Now we apply the limit. This is x approaching 0 from the right side, x times ln x, which is limit as x approaching 0 from the right, ln of x over 1 over x, which is limit as x approaching 0 from the right. Now you take the numerator derivative, also denominator derivative, and then plug the value 0 plus. So which is limit as x approaching 0 from the right. Derivative of ln x, numerator is 1 over x. Derivative of denominator, so what is 1 over x derivative? It can be written as x to the negative 1 derivative. So by power rule, it's negative 1 x to the negative 2. Negative 1 x to the negative 2, which can be written as 1 over x squared with the negative sign, which is limit as x approaching 0 from the right. Now, if you simplify, it becomes x squared over x, which is negative x. Because x approaching 0 from the right or left, it has to be equal to 0. So the value of the limit is equal to 0. So the indeterminate product has actually has a value which is equal to 0. So we saw indeterminate quotient, then we saw indeterminate product. Now we are going to see indeterminate differences. So if limit is x approaching a f of x equal to infinity, and limit is x approaching a g of x equal to infinity, and when we get the difference, limit as x approaching a f of x minus g of x would be limit as x approaching a f of x minus limit as x approaching a of g of x. Both values are infinity minus infinity kind, so it is indeterminate difference. Again, we need to bring this into quotient form. Only then can we apply L'Hopital rule. It's called an indeterminate form of type infinity minus infinity. Again, we can try to convert the difference into quotient by using the following techniques. So you can apply for this quotient, for this difference, you can apply a common difference. Or you can apply rationalizing. Or you can apply factoring to. And then it can be brought to 0 over 0 or infinity over infinity, which is an indeterminate quotient. Let's try an example of this kind. Limit is x approaching infinity e to the x minus x. So if you plug and play, meaning if you replace x with the value infinity, it's e to the infinity minus infinity, e to the infinity. So how does an e to the x graph looks like? This is our e to the x graph. So as x approaches infinity, where does e to the x approach to? It approaches infinity as well. So the e to the infinity is infinity minus infinity. Infinity minus infinity is neither 0 nor infinity. So it is indeterminate difference. So we have to bring it to indeterminate quotient. So the trick that we do is a bit of algebra. So take e to the x minus x. You can either pull out e to the x or x. I'm going to write this as e to the x over x minus 1. Is it right? You can distribute and check. So what is x times e to the x over x? So it is e to the x. What is x times negative 1? That is x, negative x. So it is actually e to the x minus x. So I'm writing the given problem in the following manner: x times e to the x over x minus 1. Now we have to apply the limit. So limit as x approaching infinity of x times e to the x over x minus 1. So with this can be split this up into two parts, like limit as x approaching infinity of x. Then the other term is limit as x approaching infinity of e to the x over x minus 1. So let's focus on this. We'll call this step as 1. We will come back to this. Then we will focus on this expression and its limit because it's a quotient. So consider that part. Limit as x approaching infinity of e to the x over x. We directly plug and play. It is e to the infinity over infinity, which is indeterminate quotient. So what do? We apply L'Hopital rule. X approaching infinity, e to the x over x, which is limit as x approaching infinity, derivative of e to the x over derivative of x, which is limit as x approaching infinity. It is e to the x, derivative of e to the x is e to the x, derivative of x is 1. So now if you plug and play, it will become infinity. Okay. So we are going to use this information in step 1, in this step, right? So limit as x approaching infinity of e to the x minus x is limit as x approaching infinity of x times limit as x approaching infinity of e to the x over x minus 1. This is from step 1. So the first part is simple, it's infinity. Then now in this part, we have already evaluated this limit, which turned out to be infinity. So it is infinity minus 1. So infinity minus 1 is infinity. So infinity times infinity is also infinity. So the answer to this indeterminate difference is actually infinity. So what are indeterminate powers? So we saw indeterminate quotient, we saw indeterminate product, we saw indeterminate difference. Now we are going to see indeterminate product. So consider limit as x approaching a f of x to the exponent g of x. The limit of f of x as x approaching a is 0, and limit of g of x as x approaching a is 0 as well. Now the indeterminate form is 0 to the exponent 0. Now limit is x approaching a f of x equal to infinity. Limit is x approaching a g of x equal to 0. Then it becomes infinity to the power 0. Limit is x approaching a f of x equal to 1. And limit is x approaching a g of x equal to plus or minus infinity. Then the type becomes 1 to the exponent infinity. So each of these three cases can be treated either by taking the natural logarithm. In that case, we will let y equal to f of x to the exponent g of x. Then apply limit. So it will become ln y equal to g of x ln of f of x. There is a typo there. So we will be applying then derivatives on either side, and then we will apply logarithmic differentiation and we can solve it. So you need to remember that when base is a function, the exponent is also a function to the exponent function. So apply logarithm. When you find the limit. Okay. So calculate limit as x approaching 0 plus 1 plus sine of 4x to the exponent cotangent x. The first we will directly plug and play, and then we will take the logarithm on both sides. So let's see what happens if I directly plug and play. Limit as x approaching 0 from the right, 1 plus sine of 4 times 0, where 0 is applied from the right side, and cotangent 0. So it becomes limit as x approaching 0 from the right. That is 1 plus sine 0 is 0. to the cotangent 0. What is cotangent 0? Cotangent, tan 0 is 0. So cotangent is its reciprocal. So it will be infinity. So it is of the form 1 to the exponent infinity. So it is indeterminate power. When it comes to indeterminate power, it is one of these kinds here. So it is actually this kind. Now we are going to apply ln on both sides. First, let's write y equal to the given expression. 1 plus sine of 4x to the exponent cotangent x. So take ln on both sides. So ln of y equal to ln of 1 plus sine of 4x to the exponent cotangent x. So ln of y equal to cotangent x times ln of 1 plus sine of 4x. Cotangent x is, after all, 1 over tan x. So ln of 1 plus sine of 4x. Cotangent, which is 1 over tan x. So tan x goes in the denominator. Now, x is approaching 0 plus. Let's try to apply the limit. Limit is x approaching 0 from the right side of ln y. So its limit as x approaching 0 from the right of ln of 1 plus sine of 4x over tan x. So if you plug and play now, this ln of 1 plus sine 0, 4 times 0, divided by tan of 0. So it is sine 0 is equal to 0. It's ln 1 over 0. So it is actually 0 over 0 again, indeterminate quotient. So now what do? We have to apply L'Hopital rule, which is limit as x approaching 0 from the right. We have to apply the limit, the derivative of the numerator over the derivative of the denominator. Which is limit as x approaching 0 from the right, derivative of ln of something. So derivative of ln of any function is 1 over that function times derivative of that function. Kind of chain rule. So it is ln of a box here. So that box goes in the denominator. Then the derivative of the box, the derivative of 1 is 0. Maybe we want to write that. Divided by derivative of tan x, which is secant square x. So it is limit as x approaching 0 from the right. Derivative of 1 is 0. Derivative of sine of 4x is 4 cosine of 4x divided by 1 plus sine of 4x times secant square x. Now you try to plug and play. So it is 4 cosine of 4 times 0 plus, of course. That's 1 plus sine of 4 times 0 times secant square of 0, 0 plus. So cosine 4 times 0 is cosine 0. The cosine 0 is 1 divided by 1 plus sine 0 is 0 times secant square of 0, which is 1. Cosine 0 is 1, therefore it's reciprocal. which is equal to 1. So it is 4 divided by secant squared 0, which is equal to 1 squared, so which is 4 over 1, which is 4. But keep in mind, this is not the actual answer here. What we are doing is the limit of ln of y. So we have to get to y. Y can be written as e to the ln of y. That's another way of writing y, isn't it? Because e and ln are inverses of each other. So we do this because we know the limit only for ln of y. So when you do limit as x approaching 0 plus, so limit as x approaching 0 from the right equal to e to the y, limit as x approaching 0 from the right. E to the 0 is equal to 1. E to the 0 equal to 1. So it is limit as e to the ln y where x approaches 0 plus. So limit as x approaching 0 from the right, e to the ln y, but ln y equal to 4. The ln y equal to 4 in the limit. So it is equal to e to the 4. So what we have done, and this is e to the 4 is the answer to this problem. The limit as x approaching 0 from the right of the function. What is the function that we considered? 1 plus sine of 4x to the power cotangent x equal to e to the power of 4. So I've done some problems in this exercise in the section videos. Please refer them. And this problem is done. Also, this problem is done. This problem was shown already. So all these problems are done in the section videos. Please check them out. So maybe we can do one problem of this kind, either 9 or 13 in this video. Let's try 9. Find the limit. Use L'Hopital rule where appropriate. If there is a more elementary method, consider using it. If L'Hopital rule does not apply, explain why. We'll do 9, problem number 9. Limit as x approaching 4, x squared minus 2x minus 8 divided by x minus 4. So by any chance, if you directly plug and play, so meaning substitute x equal to 4. So it's 4 squared minus 2 times 4 minus 8 divided by 4 minus 4, which is 4 squared, which is 16. Then 2 times 4, 8 minus 8. So it is 16 minus 16, 0. So it is 0 over 0, which is indeterminate. We notice that it is a quotient. So what is then you know that you can apply definitely L'Hopital rule, which I show in a bit. But the problem tells you that if there is any elementary method, use it. Factoring is the elementary method we are going to use. So limit as x approaching 4. The numerator can be written as x minus 4 times x plus 2 divided by x minus 4. You can cross these out, which is equal to 4 plus 2, which is equal to 6. Now, the answer turns out to be 6. Now, if we had applied L'Hopital rule, so what would have been our answer? Limit as x approaching 4, x squared minus 2x minus 8 over x minus 4 equal to limit as x approaching 4, the derivative of the numerator over the derivative of the denominator. So we get 2x minus 2 divided by 1, where limit as x approaching 4. So it is 2 times 4 minus 2, which is 8 minus 2, which is 6 also. So whether you do the problem by elementary method or by L'Hopital method, the answer should turn out to be the same. So as I said, please watch the rest of the videos for problem number 30, 56, and 65, which are also part of your practice exam. Hope this video helps. I'll see you guys for my next video on section 4.5.